What specific problem does your method aim to solve regarding large language models and the concept of understanding?
Our method aims to solve the problem of verifying the stochastic parrot phenomenon in large language models, LLMs, which questions whether these models genuinely understand concepts or merely memorize and regurgitate information based on correlations. We employ a summative assessment approach, inspired by educational psychology, to quantitatively measure the understanding of LLMs through the Physico task, which assesses both low-level and high-level understanding of physical concepts. Our findings reveal that while LLMs perform well on low-level tasks, over 95% accuracy, they significantly lag behind humans, approximately 40% accuracy, on high-level understanding tasks, thereby providing evidence that LLMs may not possess true comprehension. This disparity highlights the intrinsic limitations of LLMs in achieving deep understanding, as they struggle with tasks requiring higher cognitive skills beyond mere memorization. Ultimately, our work establishes a framework for evaluating the understanding capabilities of LLMs, addressing a critical gap in existing research.
How does the proposed method, Physico, work? Please illustrate it step by step, explaining its components such as the low-level and high-level subtasks.
The proposed method, Physico, is designed to assess the understanding of physical concepts in large language models, LLMs, through a structured approach based on summative assessment principles. First, Physico includes two types of subtasks, low-level and high-level understanding tasks. The low-level subtasks are presented in natural language and focus on measuring the LLM's memorization abilities, where models are evaluated on their accuracy in recalling definitions and core properties of physical concepts, achieving over 95% accuracy. In contrast, the high-level subtasks utilize abstract representations in grid formats to challenge the model's deeper understanding, requiring them to apply and analyze concepts rather than merely recall information. This dual task structure allows for a quantitative comparison of LLM performance against human understanding, revealing significant performance gaps, particularly in high-level tasks, thereby validating the stochastic parrot phenomenon in LLMs.
Can you provide a simple example to illustrate how Physico evaluates the understanding of a concept like gravity? Walk through the main algorithm steps using this example.
To evaluate the understanding of the concept gravity using Physico, the process involves several key steps. First, a low-level understanding subtask is designed where LLMs are presented with a definition of gravity, such as a force that pulls objects with mass towards each other, and asked to identify the concept from multiple choice options. This tests their memorization ability, and LLMs typically perform well, achieving over 95% accuracy. Next, for the high-level understanding subtask, LLMs are presented with abstract representations in a grid format that illustrate core properties of gravity, such as the inverse square law or the motion of an apple falling from a tree. This subtask challenges LLMs to apply their knowledge beyond mere recall, and results show that they lag significantly behind human performance, confirming the stochastic parrot phenomenon. Thus, Physico effectively measures both low-level and high-level understanding of gravity through these structured tasks.
What theoretical or practical benefits does using Physico offer over existing methods for assessing understanding in LLMs?
The Physico task offers significant theoretical and practical benefits over existing methods for assessing understanding in LLMs, by employing a structured approach based on summative assessment principles and Bloom's taxonomy. Theoretically, it provides a clear framework for measuring different levels of understanding: low-level memorization and high-level deep comprehension, which allows for a more nuanced evaluation of LLM capabilities. Practically, Physico includes diverse tasks that challenge LLMs with both natural language and abstract representations, effectively highlighting the stochastic parrot phenomenon by demonstrating a substantial performance gap between LLMs and humans, particularly in high-level understanding tasks. Additionally, the task design ensures validity by incorporating varying difficulty levels and aligning closely with the targeted concepts, making it a robust tool for evaluating LLM understanding. Overall, Physico establishes a comprehensive benchmark that not only assesses LLMs' knowledge recall, but also their ability to apply and analyze concepts, thus advancing the field of NLP evaluation.
How did you validate or test the effectiveness of the Physico tasks? Describe the experimental design, the metrics used, and the datasets involved.
To validate the effectiveness of the Physico tasks, we designed a series of experiments that included both low-level and high-level understanding subtasks based on Bloom's taxonomy. The experimental design involved evaluating state-of-the-art LLMs, such as GPT-3, 5 and GPT-4 on their ability to recognize physical concepts from definitions and images, low-level subtasks, and to comprehend abstract representations of these concepts, high-level subtasks. We employed accuracy as the primary metric for performance evaluation, measuring how well LLMs could answer questions related to the core properties and applications of physical concepts. The datasets included a collection of 1,200 paired grid examples for the Physico core set and 200 instances for the Physico associative set, which were manually annotated to ensure diverse and challenging representations of physical concepts. Additionally, human evaluations were conducted to assess the quality of generated descriptions, further validating the LLM's understanding capabilities against human performance benchmarks.
What specific results were achieved when applying your Physico framework to the LLMs? Please provide quantitative findings that highlight the performance differences observed.
When applying the Physico framework to evaluate LLMs, we observed significant performance differences between low-level and high-level understanding subtasks. Specifically, state-of-the-art LLMs achieved over 95% accuracy on the low-level understanding subtasks, which assess memorization and recall of physical concepts. In contrast, these models lagged behind humans by approximately 40% on the high-level subtasks, indicating a substantial gap in deep understanding, as humans scored above 90% accuracy on the same tasks. Additionally, our analysis revealed that the challenges faced by LLMs in high-level subtasks stemmed from the intrinsic difficulty of deep understanding rather than the unfamiliarity of the task format. This quantitative evidence supports the argument of the stochastic parrot phenomenon, demonstrating that while LLMs excel in rote memorization, they struggle significantly with tasks requiring higher cognitive skills.